So, hello everybody, please take a seat. There are some seats here. So welcome to the second track of the IEEE Artificial Intelligence Symposium. So you probably met me yesterday. I'm going to introduce myself again for those people who registered today. So my name is Yole Mokagata. I'm serving as a chair of the IEEE Santa Clara Valley Signal Processing Society chapter. And I'm also part of the executive committee who have organized this conference. And I'm also happen to be an Intel employee. So in all this role, it's my great pleasure to welcome you to this afternoon to the second part of our symposium. So the agenda today is software track. The software track has 2 sessions, so same format as yesterday, 2 sessions, 2 speakers for each session. There will be dinner and light dinner and a networking event between 4:45, 5 and 5:45, 6 p.m. in the SC12 Cafe. So you should all have 2 badges. One is the badge from the conference with your name and IEEE logo. The other one is a colorful piece of plastic. There is no RFID in there, so don't get any idea about getting inside Intel with that. You will be, both badge will allow you to go to the restroom, go inside Intel in a certain area, and also reach the cafe and enjoy your dinner. And of course, sit in this room and enjoy the presentation. So what I would like to ask you is when you leave tonight, there will be a basket toward the entrance. If you can kindly drop both badges, because we are into recycling, so as everybody is. And it would be nice if we can reuse both badges. So saying that, I would like to introduce the first speaker. So first speaker is Alex Smola. He is Director of AI at Amazon and also professor at CMU. He has worked on machine learning and statistical data analysis. And these include applications ranging from document analysis, bioinformatics, computer vision of the analysis of the internet data. He has quite a publication history. He's written over 200 papers, written 1 book, and edited other 5. He specialized on kernel, unsupervised information abstraction, fast sample using user model, deep learning, and interestingly, high scalable model that works on kind of terabyte of data and hundreds of millions of users. So of course, his CV is really long, so I'm try to make it really short for the sake of for the sake of introduction. As all the other speakers, in general, when I introduce them, I try to be very short because you guys are not here to listen to me, but you listen to them. So without any further notice, let's welcome the first speaker.
So thanks a lot, Yoli, for the kind words. And yeah, this is kind of a, well, daunting task to summarize all of what's going on in deep learning at AWS in 60 minutes. So, and to some extent without boring you, without also going too deeply. So let's give it a try, and I'll focus on a few recent things that have been happening. And so let's get started. So first of all, obviously the usual thanks, which is to the people who do the actual work. I'm just here and I'm having fun and talking, but these are the people who actually did the work. So and a lot of others. So let's start with hardware and data. And I guess anybody here at Intel recognizes that photo, right? That's a Xeon processor. Let's start with data. So if we look at data, I mean, this is like a typical user on AWS. I mean, you know, Pinterest, so they've got over 200 million users. They've been cloud native on AWS since day 1. That allowed them to scale. They deal with many petabytes of data every day. So they do image search, recommendation. They have a lot of data. Not as much as Facebook or Google, but they have a lot. Right? And that's kind of the typical case. Now, let's try to figure out a little bit why on earth has deep learning exploded so much over the past decade, right? I mean, is that a coincidence? Have people just all of a sudden gotten a lot smarter, or what's going on? So a good way to start thinking about that is to think about, you know, how computers have evolved. By the way, the timer hasn't started yet. If you could please start, otherwise I'll keep on talking for hours. So if you look at it, so in the 70s, the data sets were like, 100 observations. This was like Zachary's Karate Club or the Iris data set. This is kind of, you could write it out on a piece of paper by hand. I mean, it would be tedious, but you could do it. And 10 years later, it was like a factor of 10 larger. And then, things when, OCR data sets, MNIST and so on, 60,000 observations. I remember 60,000 data points was a big data set once upon a time. And then, with Google and the internet, well, we got to 10 to 100 million observations, mostly web pages, the web page graph and so on. And with computational advertising, we're now at, the order of, 10 billion. And then, well, with basically social networks and Facebook, we got to, easily 1 trillion, right? Because Facebook probably arguably knows around at least 1,000 things about every one of its users, so I think this is a lowball estimate. But the interesting thing to see there is that the amount of data has gone up by a factor of 10 initially, and then it started speeding up by a factor of 100 every decade, and over the most recent decade it's really exploded by at least a factor of 1,000. Part of this is also because of cheap devices like this. Okay, not that the iPhone is particularly cheap, but you can get cheap devices that have a microphone and a camera and other things in it, and they cost, the order of maybe $100. Now, memory has not increased quite that much. It's gone up by maybe between 10 and 100 every decade, but it hasn't really accelerated dramatically. So that means we need to actually squeeze more and more information into less memory, right? So we need models, if we were to, deal with this, that are fairly space efficient, which already tells you that something like a kernel method, which was a really, really cool thing in the 90s, right? Sort of 90s or 2000s kind of didn't work so well. Now the big revolution, though, that's happened is really on the CPU side, on the processing side. So 1970, the 8080 had about 100 kiloflops. Then, this was like, one of the really important chips. And then we went up to a megaflop, 10 megaflops. The Intel Core changed things and went up to a gigaflop, and this was pretty awesome. And then GPUs came along with 100 gigaflop, and the device that we just announced 2 weeks ago for public consumption, namely the P3s, have 8 Volta GPUs in them, and this device operates at in the order of 1 petaflop. So it's safe to assume that by 2020 we might be hitting considerably over 1 petaflop, maybe even on one device, right? So the key distinction is really that the amount of compute has grown disproportionately, especially in the past decade, even relative to the amount of data, which has in itself grown disproportionately relative to the amount of memory. So that means we have plenty of compute, lots of data, and not so much storage. And what that really means is that deep networks are a really good way of dealing with this data and compressing it nicely, because you need a lot of nonlinearities to store things. Linear models are just not very memory efficient when it comes to actually dealing with the information that's in the data. So, maybe in a parallel universe where memory had exploded and we didn't have quite that much data, we would happily still be doing support vector machines, and I might be writing some more kernel papers, but in this universe, we're very much in a different place. Now that has changed also on compute clusters, and there's an interesting thing there. I mean, obviously clusters have gotten bigger, and basically every decade they went up by a factor of 1,000. And that trend sort of kind of changed rather drastically around 2010. So probably the watershed was this paper by Andrew Ng and Adam Coates about a COTS HPC, basically commodity off-the-shelf HPC cluster, where basically they matched the Google Brain results with 10 computers and InfiniBand and a few GPUs, right? And what's happened actually is that by now the clusters have gotten smaller again. Now, why does this matter? Because a lot of the typical big data distributed asynchronous fault-tolerant processing frameworks that you needed for lots of moderately powerful PCs, right, or servers, aren't quite necessarily so much central if you have, let's say, 10 GPU servers with 8 GPUs each. Because they're probably not going to die during that one day that you run the experiments. So you can actually strip down and strip off a lot of the systems design considerations that you used to have for the big data things. So things like MapReduce and Spark are really the wrong paradigms to do this. In any case, this is kind of what's happened with the cluster size. The other really unfortunate thing is that the network hasn't really gotten a lot faster. I mean, if we hit 100 gigabit networks by 2020, I'll be very happy. So for instance, our latest machines that came out have 25 gigabit. Can you buy faster things? Of course, and I think a lot of companies will happily sell you some. I think Intel has a very nice interconnect, for instance. Now, within the device, NVLink, well, that's 300 gigabit per link, and if you have 6 such links per device, and you set this up in the right way, you can probably get around 900 gigabit actually synchronization speed. That's pretty nice. So what we're getting is that it's ridiculously hard to get the data off the machine where it's stored. It's very efficient to communicate within the device, and memory is very, expensive, so you can't actually store that much anyway in working memory in terms of models. And this is really the sweet spot for deep networks. So if you look at topic models, for instance, you have very, very large state spaces that you need to synchronize. And yeah, we wrote all sorts of complicated algorithms for that, which are very nice if you have that kind of models, but if you need a deep network, it doesn't help you that much. Now, of course, the world doesn't just consist of the clouds, right? I mean, there's mobile phones, there's IoT, there's embedded devices, and there's, actual just the sensors. So this year we had 2 chips that came out, and I know yesterday was the hardware session and you're just hearing hardware again, so this is kind of frustrating, but I just want to explain a little bit why we got where we got and how. And by now at least there are 2 SoCs on the market, the A11 and the 970, which offer in the order of 1 to 2 teraflops of compute on a mobile device at, I guess, between 2 and 5 watts range. So this is pretty impressive. And even on CPUs, you can probably get 10 to 100 gigaflops on ARM or other things. On IoT, well, this is the Raspberry Pis. I mean, you can by now do non-trivial signal processing. I mean, I guess everybody's seen the videos of scaring the cat with a sprinkler and using a camera attached to a Raspberry Pi to detect where the cat is. You can go further down, so embedded devices, so FreeRTOS, for instance. So this is the world where we have the dash button, or the ESP32 SoC, or you have your basically a motion detector in your house, right? And in all of those devices, you really want to be able to run advanced nonlinear processing algorithms. And the good thing is that the same trade-offs that we see in the cloud also happen here, namely it's very expensive to talk to your neighbors. Memory is very constrained. Compute actually isn't that bad if I can just quickly compute something and most of it is ephemeral, right? So the good thing is it's a very similar trade-off. Now, overall, what happens is basically we have compute growing at a really rapid pace. And so this is Moore's law, but then even further due to the architectural changes away from von Neumann. The data grows at Kreider's law. Kreider's law is the growth law for the hard disks. Why? Because your hard disk will always be full, right? Memory grows a lot more slowly because the architecture hasn't really changed that much. If anything, I mean, if you look at HBM, high bandwidth memory, that's smaller, right? I mean, there's a reason why sometimes, advanced GPUs get delayed, or why, for instance, GPUs don't only have, 12 gigabytes or something like that of memory, because it's just ridiculously expensive to squish it all onto those high bandwidth memory chips. And so we are basically at the sweet spot for algorithms that are very memory frugal. At the same time, because we get all this data, we want to go non-parametric. So we want to be able to have models that increase, get more sophisticated as we add more data. Okay. So, to put all this, high speech into something a little bit more concrete, here's what you can have fun with right now. So you can have, Intel Skylakes, and they run nicely AVX 512. So basically for int 8, you can do stuff. You can run a variety of generations of GPUs, and I'm rather happy about the Voltas because they're kind of fast. And if you really want to do things on your own, you can program an FPGA. This probably only makes sense for a very small sliver of the people who are here, but if you need something very specific, you can do it. So, well, can you afford it? Well, actually, it turns out you can. So these are the prices that half a teraflop will cost you. Sorry, half a petaflop will cost you. So this is basically a P3 8x large and costs you about $12 and a quarter. And spot prices are $6. So every time I put this slide up, the price for the spot instance goes up by $2. We started at $2, then it went to $4. Now it's at around $6. So in other words, people like those machines. But to put this into perspective, okay, so this is basically by now 1.5 to 2 cups of coffee. But the really interesting thing is for $2,500 an hour, you can get the equivalent of the world's fastest supercomputer. Okay, little footnote, subject to availability of these machines on AWS. Right, so the problem is you're probably not the only ones saying, well, okay, these would be nice, and yeah. So I can't guarantee you that you'll be able to allocate them, but we're working on that. Anyway, now that's fine, but then you still need to deal with drivers, and for instance, for deep learning, you need 4 different drivers. You need to, just get things done, and you need to compile them and so on. So we've tried to make it easy for everybody to use whatever deep learning tools they want, right? So you want TensorFlow, you get it. Caffe, you get it. Torch, Theano, Keras, PyTorch, CNTK. And I've probably forgotten 1 or 2 more. We've just recently switched to a Conda-based AMI because, well, as you get more frameworks, those things otherwise get bloated. But they have all the right drivers installed and compiled for the right instances to make sure you get good performance, right? So, and yes, it comes in an Ubuntu and basically an Amazon Linux flavor, and I guess most people will probably pick the first. Yeah. So then the question is, of course, well, now I have a machine and I can run my PyTorch or my TensorFlow or my MXNet model. But what about multiple machines? So let me ask a question. Who here in the room has set up a computer cluster at some point in their life? Whoa, this is good. This is awesome. This is probably the largest fraction I've ever seen. Usually I get 1 or 2 timid hands. Okay, this is old school. Good. Who enjoyed that? Doing it the 3rd time? Probably fewer hands. The first time was probably great fun. The second time, still okay. But the point is, at some point it gets tiring. So what you do is you do basically what everybody else does as well, namely software-defined network, software-defined entire computer clusters, and so you set up the VPC, and you mount points and everything automatically, and this can be done nicely through a CloudFormation template. Now, if you don't like that particular one, you clone it, you modify it, and you run it, right? So this way you can, in a software-defined manner, fire up a cluster of whatever machines with whatever disk images with the appropriate network configuration, and you can, through that, run a distributed cluster, do your computation, and when you're done, it tears it down, and, well, okay. So this way, you can get your supercomputer cluster for an hour. And basically, if all of this doesn't mean anything to you, you really want to use the CloudFormation template. So that brings me to the actual point of this talk, namely deep learning, right? And there are actually a lot of talks after me who will go into a lot more depth on the deep learning part. But let me just start by looking at a couple of very simple things. So this is a blog post that you should absolutely read. There's this data scientist called Joel Gross. And apparently he interviewed at the big software company. No, it was not Amazon. And you should read this blog post. You'll enjoy it. Basically, they asked him to program FizzBuzz. So I didn't know FizzBuzz before, but apparently it's an American children's game where you learn how to divide by 3 and 5, and you basically, whenever it's divisible by 3, you say fizz. If it's divisible by 5, you say buzz. So you go like 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, and so on, right? And you want to write some code. Okay, so the good thing is, of course, you basically want the programmer to distinguish between those 4 different cases. And what you would typically expect somebody to do, for instance in JavaScript, is to produce something like what's on the right-hand side, right? Perfectly good code, and it just checks, mod 3, mod 5, or mod 15, and then things are okay. Now, if you are a data scientist, and I guess Joel was utterly terminally bored by the interview question, he decided to make fun of the interviewers. And so he went off and, went to generate training data. 9 fizz, 10 buzz, 2, 15 fizz buzz. And then he extracted features, right? And then he decided, okay, fine, now let me actually code up in TensorFlow a piece of code for, training this. And it sort of got most things right. He did not get the job. No. So this is, dumb, but why would you do this? Well, okay, here's an example where it's actually not dumb. So if, you have cats and dogs, and I ask you to write a piece of code that distinguishes cats from dogs, well, I would bet you that you won't be able to write a piece of code in JavaScript, Python, C++, or whatever, that just by, your sheer amazing ingenuity will distinguish cats from dogs with high accuracy. On the other hand, by now in computer vision, this is kind of a yawner, right? Everybody does that. This is like, you take ImageNet features, you run a linear classifier, boom, done. So what that really means is we've gone from a situation where the goal, is easily accomplishable by a set of simple rules. It's now easily demonstrable by a set of examples. And every 2 or 3 year old, unless they've never seen a cat or dog, will probably say meow meow and wow wow. So on the other hand, as a programmer you can do it. So what you really would do is instead you use statistics, you use data to train the corresponding estimator. So this is programming with data. And this is really where things get exciting. Now, how hard is that? Well, let's take a simple linear classifier, right? This is basically taking all the input features, summing them up, applying some nonlinearity. And in 2013, I would hand this out as CMU PhD level. So for 10.701, for that class, I would hand it out as programming homework. Right? Now, in 2017, well, that's 4 lines of gluon code. Right? So that's probably about as simple as you can make it. And the first thing is, hey, I would like to have a neural network that is sequential. And then, by the way, add 1 layer. I mean, yeah, you could sort of kind of hack away the first 2 lines, but then it just looks ugly. And then you define a loss function, and you're done. This is it. And you just optimize, and, this is not something you would hand out as homework anymore. Okay, fine. So let's look at something a little bit more interesting like Lunette. And AlexNet looks very similar. And these were breakthroughs in 1995 or then AlexNet in 2012. And this was a lot of work. In this case, it was Jan de Ka. Later on, it was Hinton, Krzyzewski, and Sutzkever. And so how hard is this nowadays? Well, it's about 10 lines of gluon code, right? And if you look at it, it's basically like, okay, well, again, sequential combination of layers. Well, here's a convolution, an average pooling convolution, and so on, and that's it. Now, if I wanted to change, for instance, things from, oops, I wanted to get the laser, I guess. If I wanted to change things from that to ReLU, all I would have to do is change activation equals ReLU. Done, right? If I want to change the number of channels, add a few more layers, that's very easy, right? This is how far software engineering has come now. And that just lowers the barrier of entry drastically. This is one of the reasons why we're seeing such a ridiculously large number of papers now in machine learning, right? Because, I mean, by now you can, I think there's a guy from high school who did an internship at OpenAI and then submitted a paper to ICLR, right? I mean, okay, this kid is probably amazingly good, but it also shows you that the barrier has been lowered a lot, because for that PhD level homework, I don't think an undergrad would have had a really easy time at it. At least most of them wouldn't. Now, can you do interesting things with it? Yes, you can generate synthetic peer reviews, right? Okay, why? Well, because you can, right? Or you can answer questions, right? And this is like one of the more easy to understand ones. You know, what's the man swinging at? And okay, it's a racket. And so the thing is, you first need to find out, you know, what are you looking at? This is visual question answering. And this is, for instance, using memory networks on images. I mean, this is stuff we did last year. So here's a few more examples. In the first case, I mean, it just gets lucky because it really cannot count even if it's, you know, poor neural networks life depended on it. But basically, on the left-hand side, you see the image. Then it starts focusing increasingly on the relevant portion of the image. Well, it gets that right. And then, yeah, it guesses 4. That's kind of awkward. But here, actually, what's the color of the horns? You can see it working quite nicely. It comes up with some ideas of where the horns might be. It uses that to refine the estimates and says, well, probably they're up there. And then once you have that, well, answering that the color of the horns is red is kind of easy, right? So this is how far we've gotten. And there are plenty of variants of that. I mean, there are attention mechanisms. There are multiple pointers. It's a lot of really nice work that's come out of this, where we basically can reason over objects. Now, yes, there's much more. So there's machine translation, image, video activity recognition. You can synthesize things, mostly images with GANs, and every once in a while there's a paper, an article on TechCrunch about how creepy the latest applications of GANs are, because they're really pretty. Neural art, image synthesis, question answering, as I mentioned, dialogue systems. So if you look at, you know, things like Alexa or Siri or Google's version of that, right? I mean, they all have deep learning somewhere underneath. Speech recognition, obviously, speech synthesis, search and recommendation, also logistics, basically, you know, which card should go next to move where to help that picker, right? All those things, I mean, they require and use at some point deep learning. So that brings me to a slightly more sensitive point of this entire talk, namely, or let's say the elephant in the room, you know, why on earth are we doing yet another deep learning API, right? I mean, you know, don't we already have so many of them, right? I mean, there's Caffe, there's Caffe2, there's Torch, there's PyTorch, there's Theano, TensorFlow, CNTK, Keras, Paddle, Chainer, Deep Learning for J, Played, and probably I've forgotten another 10 of them, right? Right? So, you know, why bother, right? After all, you know, wouldn't it be great if there was just one and that was it, right? Well, almost. Sorry, I've kind of given this away. So what's been happening, actually, if you look at, you know, the evolution of deep learning frameworks, I mean, yeah, once upon a time there was Theano, and then Caffe came along, and Caffe simplified things a lot by actually having a lot higher performance and having, you know, better, you know, model definition, and then CNTK, and then, you know, there's Keras, which kind of was the first human readable version. It was actually intended to be, you know, sitting on Theano. Then TensorFlow, which was an industry strength supported framework supported by Google. And then there's Chainer, which is popular in Japan. And MixNet basically combined a number of those features. Basically, the imperative part of, you know, you write code and it executes, and the symbolic setting from, you know, essentially Keras and TensorFlow. And then PyTorch came along, and PyTorch essentially cloned the Chainer API, modified it a bit, and then we did the same thing. We basically cloned the PyTorch and Chainer API took the best ideas from MXNet underlying, took the layer definitions from Keras, and that led to Gluon. So Gluon is basically our imperative API on MXNet. You can mix with the rest. It's called MixNet for a reason. And Microsoft were happy enough with that they decided, yeah, that's a good idea, let's join it. So at some point, you'll be able to run Gluon on CNTK. Now, why? Well, let's look at Caffe. So if you want to do something like ResNet 101, you're probably not going to write 4,000 lines of code. You're going to write a little script that will generate those 4,000 lines of code because protocol buffers are, in theory, human readable. Well, not in practice, they're kind of painful. I mean, don't get me wrong, protocol buffers are amazing, but 4,000 lines are painful. Then on the other hand, if you want to write up an optimization algorithm, if you try to implement Atom in TensorFlow, that's around 300 lines of code. In Gluon, it's maybe about 12. Part of the reason is that in one case you can write it in an imperative way, how you would write your research code, and in the other case you basically need to define your operators and so on, and that makes things interesting. Now Keras has very, very nice, clean layer definitions, and it's very simple, and you probably, if you recall what I showed you before in Gluon, this should look very similar. It's basically model sequential, add a layer, add a layer, add a layer, and then in the end just compile that graph and fit it. So if you don't need to debug what's going on while the code is running, this is pretty good, but it's not so easy if you have dynamic structures, right? Like trees and so on. So PyTorch and Chainer got this right. It's very flexible, but if you compile the code and so on, it may not be quite as fast. Enter MixNet. So it has a nice symbolic definition for layers, and it has an imperative tensor computation, but it's not fully imperative, and it turned out that a lot of our users really wanted that fully imperative style. So we decided to give it to them. Now, before I discuss a lot of why you would do that, let me give you a little bit of an example of why you would care. So what I've shown here is a nice, decorative symbolic program. So you have like variable A, variable B, you multiply those two, then you add 1 to this variable, you get variable D, and then you go and compile that graph, and then you plug it in. Okay. And this is very nice because, well, I can immediately compile out C because, C and D share memory, so I don't really need to keep C around if I need to compute D, or I can do an in-place operation. Depending on how things go, I could maybe even do that on A and B. And ultimately, this offers a lot of opportunities for optimization at compile time. This is great. But it's really hard to debug what's going on inside, especially in terms of convergence, not so much just in terms of, well, is my code, so to say, technically correct, but is that model actually going to work? And that's something where, for instance, otherwise you need stuff like TensorBoard to actually look inside your model. And you can't just run Control-C, let me look at where the variables are, and then continue, right? This is not so easy. And you can't really do this nicely with native code. So, alternatively, you just go and write code as you would expect it, right? Define variables A and B. You multiply them, you print something out, some debug statement, maybe you fire up matplotlib or bokeh, and you add things together, and this is very straightforward. You can have control flow, and it's a pain to optimize. I think we've come up with an acceptable solution for it, acceptable in the sense that it's almost good enough, and I'll show you what I mean with almost good enough a little bit later, but basically by using a JIT compiler, just-in-time compiler, to compile the pieces that are essentially static parts of the graph, and to dynamically execute the pieces that are dynamic. And this is nicely hidden underneath the, the framework, so you can do things. I'll show you some examples. So what happens is basically if you have the same compute graph being executed over and over, and if you do this in Python, it's very, very awkward. With Python it's slow, it has a global interpreter lock, and while you don't care about that for a single small, slow GPU, you do care a lot if you have this on an 8 GPU, 1 petaflop machine, because Python will slow you down. It's kind of ridiculous if you have, this amazing piece of hardware, and then a single thread on a single core is what essentially kills the performance on this beast, right? So what you do is you basically want to get rid of your Python interpreter wherever you can. And what you do is you basically say, well, hey, here's that graph. I know that I'm going to execute it many times over. For instance, your ResNet or your Inception or whatever, or your DenseNet. You say, please go compile. And now it will no longer actually call the Python interpreter for that piece of code, but it'll just automatically invoke the corresponding compiled version of that graph. And you can use that to serialize the network. You can dump things out into, well, Core ML or JSON overall, or you can, have fun with Onyx, and you can import Onyx, so you can do things with it. Right? So that's kind of nice and pretty, but what's going on the back end? So here's our trusty network again. So we have that graph from before. Here we have our corresponding, compute graph. And then we have some, symbolic part. It's on the left. On the right up here. And then you basically get that graph. And so the interesting thing is that this variable c is now shared, and you can just use that. So basically the backend, which is all C++, needs to be able to take both the symbolic and the imperative pieces, combine them, and then jointly execute the resulting graph. That lets you do some interesting things in terms of memory layout, operator fusion, and a lot of automatic parallelization. You can do liveness analysis, you can share space between variables. Suffice it to say that this actually helps a lot in terms of reducing memory consumption. Now you might wonder, well, why are we so crazy about memory consumption? That has something to do with where this all started, right? So we started as basically a poor professor at CMU. We were hand-assembling machines. And so we had 50 hand-assembled machines with like 150 or so GPUs. And a lot of them were, of the GTX 750 type with 2 or 4 gigabytes of memory, right? This is not the Teslas, but the really small and crummy GPUs. So if you wanted to do any deep learning on them, you had to actually make sure it fit. So and likewise, our network was pretty awful. This was gigabit Ethernet, right? Not 10 gigabit, not InfiniBand or anything. So that really awful hardware turned out to be a really big blessing in disguise, because it forced us to reduce memory footprint. It forced us to be efficient. And that's actually what's helped us ever since. Now, there are a couple of other things you may want to do, like operator fusion. So if you have multiple operators, you want to fuse them together, you compile this down such that then actually that entire fused operator gets executed. Not a big deal if you have a slow GPU. It's a big deal on a fast one. Why? Because if you actually execute individual kernels, right, you're talking about microseconds to fire up a kernel on a GPU. Now, if that takes microseconds and executing that kernel takes microseconds, you're paying a significant overhead for the actual kernel. So fusing things helps. And yeah, it helps a bit. Like, this just adds up. Now, of course, ultimately, one GPU is good, many GPUs are better, right? So how do you parallelize? And we've settled on something that, from a systems point of view, is a yawner, right? So bear with me, and I'll explain to you why we picked something very utterly boring. But essentially, here's what we do, right? I mean, you just take, one mini batch per GPU per machine, and you basically aggregate the gradients between the GPUs on the machine and then between machines. You update the parameters and you broadcast it back, right? And so in math, that's what's going on. And then, you do some intelligent updates, and, maybe you just add up, gradients, or you do something that, squishes them and momentum terms and so on. And I think we have like 12 or 13 different optimizers. You can pick one and probably implement another one easily. But this is sort of, by and large, the general template of what you could do. Now, here's an interesting challenge, right? So as we get more GPUs, more machines, we need a larger mini batch. Why? Because otherwise we have to synchronize too much, right? The other thing is, we need to synchronize the data, the model, the gradients, so there's interesting things going on. So what you could do is, you could do the model parallel version, and this is something that initially, for instance, they did on AlexNet because one GPU wasn't big enough, where you would compute parts of the model on one, parts of the model on the other GPU. And then it leads to all sorts of really expensive things because your PCI Express bus is a lot slower than your GPU. To do the dumb and simple thing is to just, send the data to each GPU individually, you compute your loss gradient, and you aggregate. Now, about synchronization. Asynchronous processes are a lot more efficient, and if you have 1,000 machines with GPUs, you almost certainly want to do that, because then, compute and synchronization and broadcast, they don't need to be fully synchronous, and you can do some things overlappingly and so on. And this is much more efficient. And now, on the other hand, if you have, 10 machines that are, high-end machines and nothing else is going on them, you can pretty much assume that they're all pretty much the same speed, so you don't need to do a lot of expensive, as in, in terms of programming, expensive operations on the system side. You can keep it quite dumb and simple. And that actually buys you performance. It's like, well, you do these expensive things if you really need it, but it's like, walking around in the city with a seatbelt. You don't need one. You only need one if you have a car. So the pragmatic strategy, therefore, is, basically compute the gradients on mini batches, aggregate, broadcast back, and it works fine, and it makes the code very simple to understand. So in pictures, data gets sharded onto servers, split up onto GPUs. They compute the gradients. They send the gradients back to the servers. It gets aggregated there. Actually, on a DGX1 or a P3, you aggregate it within the GPUs because they're much faster, but that's a minor detail. You then send it to a parameter server for further aggregation. Parameter server aggregates, sends it back to the servers, and you're done. So that's the parameter server. It's been around for, almost a decade now. And it's really just a key value store where the put and the get operations have been overloaded. And because it's so dumb, simple, it's actually very popular because you can very easily reason over it. Now, in practice, it's not quite that dumb and simple, because if you get an interesting piece of hardware like a P2 server, which has this, let's just say, somewhat unique design in terms of PCI Express bus switches, you actually have those GPUs with a heavily bandwidth constrained interconnect in here. So if you just do things naively to try and push everything to the GPU, to the CPU, it's not going to work, so you need to actually design meaningful synchronization algorithms. Now, unfortunately, the algorithms that you design for this don't work for that, right? This is a very different network. And that probably won't work for a lot of other things. So what you may actually want to do is to think of how you can synthesize such synchronization algorithms automatically. Stay tuned for that part. But yeah, suffice to say it can be done. And then you go and basically synchronize between the GPUs and the CPU. And then there's a network switch which has lower bandwidth still. So you basically have a multiple tier parameter server. You basically have one parameter server within each box and then one that keeps everything in sync. Okay, so this sounds all really complicated, even though I claimed that let's keep things simple. Well, as simple as you can get away with. Well, it actually works, right? So this is on 16 GPUs. That's a P2 16x large. That's basically, bunch of old Keplers. You get almost perfect scaling. So what I'm showing here is the time it takes to process per batch. And we basically kept the number of images per batch constant as we increase the number of GPUs. So in that sense, it's weak scaling, right? And the perfect plot would be a horizontal line. It's not quite horizontal because, well, you pay a little bit of communications overhead. Since you can do some of those things in the background, it doesn't hurt you that much as long as the communication doesn't take longer than the rest. But you can see that it significantly impacts you, for small mini batches. So in other words, if you have a slow network, you just need to increase your mini batch size. Now, you might be concerned like, well, doesn't that lead to poor conversions? And I'll answer that in a moment, but I want to show you something else. Because single machine is boring, multi-machine is a little bit more interesting. So this is, I think, 8 GPUs with per machine with 16 machines. And you get 115-fold speed up on 128 GPUs. And it's the same idea of the plot, right? So that scales. Now, does it actually work? So what you basically need to be concerned with is, as you increase the number of GPUs, well, I need to increase my mini batch size. So at the very least, I need to have one observation per GPU. So that's 256 images per mini batch. Now, everybody knows this is, ridiculously inefficient, so you want to increase it to maybe, 10 images per mini batch or 20, which unfortunately leads to a mini batch size of, 5,120. A lot of beginners' data sets are smaller than that. Okay. And what you can see is that in terms of accuracy, actually that number doesn't really change. So the reason why this happens is because you basically need to increase your learning rate for larger mini batches. Why that? Because concentration of measure leads to a reduction of variance as you increase your mini batch sizes. Now, here's the bad news about parallelization. If you try to parallelize MNIST, it's not going to work very well. Because MNIST is a very boring and simple problem. And on those very boring and simple problems, all the gradients pretty much look the same. On the other hand, if you have something like, let's say, for instance, ImageNet, or you have a machine translation problem, or you have something, that's equally interesting, where you actually get the large diversity in your gradients. In other words, you have non-trivial eigenvalues in the official information matrix, scaling up is good enough, and you can do it. Okay, so what that means is, quite simply, if you want to get a certain level of accuracy, more GPUs will let you get there faster. Okay, well, fine. So let me just compare to a few things. So what we did is we compared the symbolic and the imperative version of MXNet, so in other words, Gluon and MXNet, on 1, 2, 4, and 8 GPUs, so on the old P2 8X large Keplers. And what you can see is that, so we compared to two other popular frameworks. One is a very popular imperative framework, the other one is a very popular symbolic framework, and yeah, I guess you can guess what they are. But basically for a single GPU, it doesn't really matter very much, right? You're basically seeing like 5 to 10% difference. But actually, on those, the scalability isn't really so much of an issue anyway, because otherwise you would have requested 2 GPUs, or 4 or 8. What you do see is that as you increase the number of GPUs, you see that gap actually opening up quite a bit. Now, why am I saying that we're not quite there yet with Gluon? Because it's not quite level yet, right? It's not clear whether we ever will draw exactly level, but there's still a gap to be worked on. This is basically still, the demons of Python that we need to exercise from that, right? Are we doing better than the rest? Well, this is a fully symbolic framework. It's an imperative one, yeah, but not good enough yet. But, these are boring pictures. That's, old hardware from last year. How about hardware from this year? So these were experiments that we ran within about a week of getting our hands on the P3s. So we had to recompile with CUDA 9 and do a lot of other things. And these are results using FP16 afterwards. The black line is the baseline from a P2 8X large server, and this was run on a P3 8X large. Right? So they're about the same cost. A little bit more, but not much. So what you can see is that yeah, you get about a 6.4 times speed up. And most likely, that number will go up further after we do a lot more tuning. But this is basically straight out of the box. My guess is the TensorFlow numbers would look not too dissimilar. But we just didn't have time yet to benchmark and tune that. Now, of course, computer vision is so last year, right? So what's happening now? Well, basically, what if we have dynamic structure? So if you want to do dynamic reasoning on objects like text or other things, like tree LSTMs, right? And I'm just picking tree LSTMs as an example, not because they are the best network structure, but because they very easily explain what's going on. You basically have a dependency graph where the number of ancestors varies at different places. So it's basically a classical computer science tree structure. And then you may want to do interesting things in terms of efficiency because basically you want to make sure that you're grouping similar operations together. For instance, all operations with 3 operands, all operations with 2, and so on. And if you do that, you get about a 4-fold speed up. So dynamic batching. This is the good news. So and it also means there's still a lot of work to be done, right? Because this is essentially straight out of the box. This is if you do things a little bit more efficiently. I think TF Slim does something quite similar. There's still a lot of work to be done. This might be an indication for it. So C4 large. Basically, on a GPU instance, these numbers aren't that much better. In other words, even though by doing various tricks you can accelerate things in Python a lot, the Python interpreter is still a big pain, and, well, stay tuned. So with that, I think I've actually run out of battery quite literally. And so the last slide is here. Sorry, I've somehow managed to empty that. But basically, the summary is I hope I gave you a bit of an overview of what we've been up to over the past few months. If you want to find out more, we're actually writing a new book, so gluon.mxnet.io. By now, it's around 300 pages. It's all Jupyter notebooks teaching deep learning in a way where you can just, go and, play with it. And yeah, this might help you. And then there's a forum, and if you speak Chinese, there's a Chinese discussion forum that's actually very, very lively. And yeah, obviously we're hiring like everybody else, so you're going to see that part from, I guess, all the speakers. At least if you haven't, then I guess every other speaker will add it now. So thanks a lot for bearing with me for those 60 minutes, and let me know if you have any questions.
Good if you guys and gals can come to the mic, and then we can go from one to the other. Go ahead.
Thank you for the excellent talk and very inspiring. So I have a question. Should we discuss to start teaching 6th graders with Gluon as a 3rd language? I mean, first language is English. The second language is whatever the business language for the nation they're going to do business in, right? The 3rd language sounds like should be Gluon. So what do you think?
Well, the first, thanks for that. I think we'll have to teach them Python first. Secondly, yeah, there's a Chinese version of all of this. So, yeah. So I have a few more years until I can try this with my son. I mean, he's in 6th grade now. Yeah, I still need to teach him a little bit of math before I can introduce him to deep learning. Yeah. So maybe 6th graders, not quite yet. Maybe you have a very bright one at home. You can try.
Thank you.
Hello, thank you for the presentation. When it comes to computational power and these days cloud computing, I think AWS is the leader, as everybody appreciates. I wonder, what's your thought on the future? Are you really bullish on machine learning, deep learning, or you think it's going to be a breakthrough at some point? And what's your futuristic view of the whole thing?
Okay. Oh wow, that's a heavily loaded question. So I think what we're going to see is that a lot of code that now has parameters in it will turn into code where these parameters are tuned in some way based on data. I mean, let's face it, most of us, when they write code, there are a couple of fudge factors. And it's like, well, we make an educated guess, like, 10 iterations got to do, right? Or something like that. So these are things that will get tuned. We'll also see cases where, we'll see a fusion between, standard programming and what you can do with statistics. This is actually really exciting. And to some extent, you have, for instance, things like the neural Turing machine or the neural programmer interpreter and, similar very nice things that came out of DeepMind, right? So these are starting points. I don't think that they necessarily are a perfect way of going about it, because they kind of throw away, 30, 40 years of, program synthesis and verification and all of that, right? But essentially, you're starting to see progress on both ends, right? You see people trying to automatically synthesize code, to learn how to lay things out, to learn how to, even do deep networks themselves, right? Some of those things are ridiculously compute intensive. So we're nowhere near there yet, but I think this is going to be quite exciting. The second thing is you can now do a lot of things that would be kind of straightforward for humans, also some things that are a little bit less straightforward for humans, with machine learning. And that lets you automate a lot of things, right? This lets you automate a lot of menial jobs, right? So for instance, if you look at the announcements of self-driving trucks that just came out yesterday, right? It's probably not a good time to be a trucker, right? It's maybe not a great career to, start a career in stacking shelves, right? Because maybe at some point robots will get quite good at that, or to work at the cash register, right? So there's a large number of such jobs that probably will be automatable by devices that don't get tired, right? Now, what's the next big thing after deep learning? Well, I don't know, but I can surely tell you that this is going to be exciting at least for the next 5 years from now. And beyond that, I don't think any of us has a good guess.
20 years.
So these environments are really complex, many languages, clusters. What kind of tools, can you tell a little bit about the tool set that you use to look at bottlenecks, to profile, to navigate multi-languages?
So this is probably a real pain point. And so I think in CUDA, you use NVIDIA's tools, and there are tools that you use for profiling Python. There are tools that you measure the network. There are tools that we have inside. Internally. And right now, essentially performance and profiling tools are probably nowhere near where they should be. This is,
a pain.
So let me put it this way. If you have some suggestions on how to make this better, please talk to me.
Thank you. I was hoping.
Thanks.
So probably we can make that as the last question.
Yeah, I have a question regarding it seems to me your glue on the API is kind of a very high level. Mm-hmm. And you're going to constrain some people to work on it for the innovative, for different models, different learning algorithms, or do you primitive, or what kind of define?
Okay, so I showed you the sort of the really easy level, and we've worked very hard to make it really difficult to screw up at the easy level, but you can actually define things, like you can define layers, you can define operators. You can actually, which is pretty cool, define essentially entire operators on that otherwise, you would need to write CUDA code by just writing the math and writing the layout scheduler by using NNVM TVM, right? So this way, rather than writing CUDA code, you're writing stuff that looks probably more like Halide. I mean, after all, TVM is more or less a Halide fork in the first place. And then we let, our compilers take care of the messy parts. But if you want to write CUDA code, you can do it. You can drop it right in. It's just that this would be a very different talk, maybe at GTC, for performance tuning of MXNet on NVIDIA, and you would see a lot of gory details like this. So, but basically the beauty of those modern frameworks is that you can actually strip out a lot of those pieces, right, and hide them, because it's so much harder to find somebody who can do detailed CUDA programming at high performance than it is to find somebody who implements or re-implements a capsule network, right? Re-implementing the capsule network was like 60 lines of code in Gluon, right? And, on the other hand, a CUDA kernel is a little bit longer. So that's actually why it's really exciting nowadays. Anyway, with those words, I think I should hand over to my next speaker.
Yeah, you address a very good scalability, very good very good issues, and but it's kind of the new network getting bigger and bigger. I don't know what's the communication between all the different components, different.
Okay, we can take that offline, but I think what's happening really is similar to what's been happening in VHDL, right? People used to design transistors, then they designed flip-flops, then they designed memory banks, and now you have much, much larger logic blocks. Do people still design transistors? Yes, but there's like one team in Intel that sits in one corner and does it for the entire company, right?
Yep.
Maybe you have two teams,
maybe
but
more than one.
Right. So that's a very specialized skill then. Anyway, I should probably now really not waste any more time.
Okay, so before you go, we would like to offer you this as a token of appreciation.
Thank you.
Thank you.
Thank you.
Okay, so let's